Have you ever considered the invisible rivers flowing deep beneath the surface of the earth, vital pathways for one of our most precious resources? Transmissivity provides a fundamental description of how groundwater flows, specifically quantifying an aquifer's ability to transmit water horizontally through its full saturated thickness. Think of it this way. Groundwater moves through porous geological formations like sand, gravel, or fractured rock. Transmissivity combines two critical factors to describe this movement. First, there is hydraulic conductivity, which measures how easily water can pass through a specific type of material. A sandy aquifer, for example, will have a much higher hydraulic conductivity than a clay layer because of its larger pore spaces. Second, transmissivity also accounts for the full saturated thickness of the aquifer. This means it considers not just the material itself, but also how much of that material is available for water to flow through. So, an aquifer might have excellent hydraulic conductivity, but if it is very thin, its overall transmissivity will be lower. This property is typically expressed in units of square meters per day or square feet per day, indicating the volume of water that can move through a unit width of aquifer under a unit hydraulic gradient. Understanding transmissivity is essential for hydrologists and water managers. It helps them predict how quickly contaminants might spread, estimate the sustainable yield of a well field, and design effective groundwater remediation strategies. Engineers often determine transmissivity values through controlled field tests, such as pumping tests, where water is extracted from a well and the drawdown in nearby observation wells is carefully monitored. These real-world measurements are then used in computer models to simulate groundwater flow. A fascinating aspect is realizing that transmissivity is not a fixed number for a geological material, but rather a characteristic of the entire aquifer system. This distinction is crucial for accurate hydrological modeling. For instance, a confined aquifer, which is sandwiched between two less permeable layers, might exhibit high transmissivity even with moderately conductive material, simply because it extends for a significant thickness. Conversely, an unconfined aquifer, directly open to the surface, will have its transmissivity influenced by changes in the water table, as its saturated thickness can fluctuate. Ultimately, grasping the concept of transmissivity allows us to look beyond just the type of rock or soil and truly understand the overall capacity of a groundwater system to convey water. This knowledge empowers us to make informed decisions about managing our precious groundwater resources, ensuring their availability for future generations, and protecting them from pollution. It helps us visualize the invisible movement and plan accordingly for a sustainable water future.
If you love learning about water, like, subscribe, and keep exploring with us.